So our first talk for the day is Edward Lee, who will tell us about
Thanks for coming. I guess that was a bit of a surprise, the microphone coming on. It sounds a little weird. You lower it, okay. I'm not sure we need the amplification in the room, actually. It's a small room. But anyway, thanks for coming. I was a little worried that no one was going to show up this morning because apparently what I think of as real time has almost nothing to do with this workshop because there was very little of it yesterday. But we'll see. Maybe I'll be able to make some connections. So let me give you a little bit of background. The work that I'm going to be talking about is work that's going on in a research center that's headquartered here at Berkeley called TerraSwarm. And it's focused on the technology of systems that integrate sensors and actuators into computing and networking systems. So this particular picture is one that's been used by a lot of people to kind of explain the idea. It comes from Jan Rabai, but the idea is that you've got the cloud backbone, you've got the primarily user interface devices, handhelds, PCs, and so on, and then what Jan called the swarm at the edge of the cloud, which are all the sensors and actuators that are then interacting with the physical world. Okay. So it's a pretty large research center. There's 9 universities involved, and it's I would say about 40% of the work is going on at Berkeley, but it covers an enormous dynamic range, all the way from people who are really primarily focused on the sensor and actuator devices, all the way up to machine learning people who are using cloud infrastructure and doing anomaly detection, like what we heard about yesterday on sensing and actuation. So the intellectual focus of this center is on what a lot of people these days are calling cyber-physical systems, because it's primarily about systems that integrate both physical dynamics through sensing and actuation with computation and networking. And the key observation is that this really underlies most of the industrial economy today. It's really hard to find an industry that isn't doing cyber-physical systems in some sense, because they're putting computing into everything. And of course the really high visibility things are self-driving cars, smart grid, manufacturing systems, biomedical systems. All of these are really very much becoming cyber-physical systems. And the interesting thing about this, from my perspective, as a research area, is that it is full of contradictions. There's contradictory requirements throughout. You need systems to be adaptable, but you need them to be repeatable because they're safety critical often. You need high connectivity, but you need security and privacy. You need high performance, but you need low energy. Okay? You need asynchrony, but you need coordination and cooperation. You need scalability, but you also need reliability and predictability. You've got laws and regulations, you've got technical possibilities. These are often very much at odds with one another, and so on. The particular contradiction that I'd like to focus on today is in the notion of what a process is. There are really profound differences between the computer science view of what a process is and the rest of engineering. The rest of engineering thinks of dynamics, the evolution of the state of a system over time, whereas computer science primarily focuses on algorithms. These are very different ways of thinking about the dynamics of a system, and they don't mesh together very well at all. And this is really the essence of what I'd like to talk about today. In my opinion, these contradictions they demand innovation, and it's a wonderful area to be doing research in for that reason. I was pretty disappointed in the talk yesterday because, in fact, Harvey perhaps led you to believe that there are no real-time problems in the Large Hadron Collider. There's just big data problems, huge data, enormous data problems, right? But what he described were not real-time problems. That's simply not true. The Large Hadron Collider is doing some enormously innovative stuff with real-time. One of their recent innovations is this White Rabbit project at CERN, where they synchronize clocks around this 27-kilometer ring, okay, to precisions of about 80 picoseconds, which at the speed of light is about this far. So that means that you ask two clocks that are 10 kilometers apart what the current time of day is, and they will agree within about 80 picoseconds on what the current time of day is. CERN uses this to orchestrate the controllers and to timestamp the sensing throughout the 27-kilometer ring, okay? You can do orchestration at a distance, two machines 10 kilometers apart, that can act in synchrony at precisions of tens of picoseconds, even though the speed of light makes it kind of impossible to coordinate that directly. This technology was used by a graduate student at CERN to expose the flaw in the experiment a couple of years ago that purported to demonstrate that neutrinos were traveling faster than the speed of light. And so this is a very profound innovation, I think, and this ability to synchronize clocks at very high precision, I believe, is actually going to pervade all of our networks. I predict that within a few years, anything that's on a network is going to have a clock synchronized with everything else that's on a network to precisions probably globally on the scale of microseconds. And in my view, that profoundly changes what you can do with distributed computing systems.
How do they tell if the clocks are synchronized?
It's extremely difficult to measure these. Okay, there's quite an art to making the measurements to determine the synchrony of the clocks.
How do they even do it?
They have to put the devices side by side, and they put 10 kilometers of cable coiled on the floor between them, okay? And then they have temperature compensated oscilloscope probes where the wire lengths are very precisely measured to be exactly the same length. They use extremely expensive hardware where the amplifiers that are used in the oscilloscope are all calibrated to very high precisions. It's extremely difficult to do these measurements. Okay.
But okay, so now,
Yeah.
what happens to these wires when you actually unravel them and they go over miles, then there are different temperature differences? Does that affect anything?
So it turns out that the clock synchronization precision depends only on the asymmetry and the latencies in the communication. It doesn't actually depend on the latency. So if the latency between a communication from A to B is the same as from B to A, then you can perfectly synchronize the clocks. Okay? So what they run Ethernet over fiber in this network, and they use the same fiber for both directions. So the temperature effects are the same in both directions.
Oh, nice. Okay.
Okay, so what is real time? All right? So in my view, real time refers to the time of the physical world, okay, which was missing in all of the talks yesterday. Nobody talked about the time of the physical world, okay? There's, of course, a rabbit hole I could go down. What do we mean by the time of the physical world? Well, you'll have to, invite Stephen Hawking to explain that one, right? So I think there's a few useless observations, and I have a handout, okay? Because I don't want to talk about these useless observations, but I've written a one-page document on why these views of time are useless. So if you'd like to read about it, I won't take the time now, okay? You see this all the time, though. Time is a resource like any other in computing. We have resources, we have to manage resources, so time is a resource. It's not. You can read the one-page paper. Okay, so let's talk about more useful notions of what real time is. Well, I'll try to go through each of these, but some of them I'm going to go through rather quickly because they all have rather different implications on how you approach the computing problem. Of course, the simplest one is just fast computation, right? If you do things fast, that does have a connection with real time in the physical world, of course. But it's not a very interesting notion of real time in the sense that, well, it's interesting because it's interesting to everybody, right? Everyone wants fast computation. So it doesn't distinguish the problem, and I don't need to take your time to talk about it. So I'm not going to talk about it. In the classical area of real-time computing, that area is primarily about operating system scheduling. Prioritized scheduling. Assign priorities to tasks, and run them in a multi-threaded environment. To me, this is also not a very interesting interpretation of real-time. It is literally the most established notion of real-time computing, but it suffers from all the problems of multi-threaded computing plus new ones: brittleness, priority inversion, non-monotonic anomalies, etc. I don't think it offers a very good solution to the real-time problem, and so I'm not going to talk about that either. So this one gets a little more interesting, and this one we did see yesterday. Okay, computation on streaming data. All right, so what do I mean by streaming data? Well, there's streaming data from the Matrix, if you remember the movie. Okay, the key idea is that the data is unbounded. It's not just big, right? It's going to keep coming at you forever. You might as well be thinking of it as infinite data, not bounded data. And in contrast to Ronit's talk yesterday, you can't do random access on the input data. You don't actually have the data. It's streaming at you from sensors, and it's going to keep coming. You don't have the whole data set, and yet you want to be able to do queries on that infinite data set. Okay? From the perspective of computing in this context, halting is a defect, not, I mean, in the Turing-Church thesis, all halting programs are equivalent. Here, it's the other way around. All halting programs are defective. You need algorithms that operate on incomplete data, and some of the best work I've seen recently, really creative stuff by Rajiv Allur at Penn, who shows how you can take algorithms that are sort of like classic search algorithms that have been developed for operating on finite data sets, even big finite data sets, and actually adapt these algorithms so they operate on infinite data sets. And there's interesting problems about how you keep the state of the algorithms bounded, even though the data over which they're operating is unbounded. Very nice work by Rajiv Allur. To me, one of the interesting things about operating on streaming data is that it implies different software architectures. So, the sort of established way of componentizing software these days is using object-oriented methods, where you bundle data and methods, and the way that you interact with a software component is a transfer of control. You call a procedure and you get a return value, and that possibly manipulates the data. That's not a very good way to componentize operations on streaming data. It's a very procedural view of a software component. And so there's a whole class of other kinds of software components that fall under the category of actor-oriented, where you stream data through the component instead of streaming control through the component. You don't transfer control to it, you just sequence data through it. It's a more intrinsically concurrent way of thinking about the software architecture. There's a lot of subtle questions that come up when you put these things together. So for example, if I think of these three boxes here as processes that are operating on streaming data, what does it mean when you have two streams of data converging on a single process? Okay, I mean, a really naive thing to do is, well, nondeterministic interleaving. Well, but that has a lot of implications that can be really problematic, right? So you might instead want, for example, to timestamp the data on these streams in order to define a meaning for the interleaving of the converging streams. All right? How you bound the state of these objects, even though they're operating on an infinite amount of data, or at least an unbounded amount of data. How is feedback handled? So the interactivity that Leonard talked about yesterday can be thought of as this kind of loop in streaming data. Okay, so these feedback loops create some interesting semantic problems. There's a lot of beautiful theory in process algebras for talking about how you for analyzing those kinds of feedback interactions. You can generalize the notion of streams to multidimensional streams. A stream, naively, is a single sequence, but you could have a partial order of components in a stream, okay, where there's dependencies between the data, but the data is progressing in multiple dimensions at once, okay? And to me, one of the most interesting things is assigning a semantics of time to these streams. So for example, timestamping the data and then treating that as part of the semantics of the stream. So I could probably give you a whole talk on each of these, but I'm not going to do that. I actually teach a graduate course that goes into this in quite a lot of detail that I'll be offering next spring. Okay, so let's go on to the next notion of real time, bounded execution time. The key issue here is that we have chosen in computing a semantics of software where the notion of correct execution of a program has nothing to do with how long it takes to do anything. The timing is irrelevant to the correctness. It's the semantics of every widely used programming language has this property, okay? So timing emerges from the implementation. When you build a piece of software and run it on a piece of hardware, then you get timing. It's not part of the design, okay? Now this has some pretty serious implications for cyber-physical systems. So one of my favorite examples of the implications comes from fly-by-wire aircraft. So the first fly-by-wire aircraft was the Airbus A320, which started flying in around 1985. And in a fly-by-wire aircraft, computers mediate the pilot commands and then directly control the actuators, and sense data can alter how the computers interpret the command. So for example, in the Airbus A320, the computers implement a flight envelope protection that makes it impossible for the pilot to put the plane in a stall. Okay? The pilot can pull back on the stick, try to pull up the nose. At a certain point, the computers won't let it happen. Actually, Airbus also dispensed with the stick, so they changed the user interface when they went with fly-by-wire. Boeing did not. Okay? One of the most recent, probably the most recent, fly-by-wire aircraft is the Boeing 787. So I heard a story from a guy who worked on the Boeing 777, which was their first fly-by-wire aircraft, the one preceding the 787. And the 777 started flying in 95. And Boeing estimated that they would be making this plane for about 50 years. Okay, that's a typical production run for a commercial aircraft. 50 years they make it. And then it flies for another 50 years probably, okay? So you're talking about 100 years of production and maintenance. In the early 1990s, Boeing stockpiled all of the microprocessors that they're going to need for the 50-year production run of the plane, plus 100 years of maintenance. Okay? Boeing 777s are selling very well right now. You can buy one if you have enough money. Okay? And the flight control system will use microprocessors that were made in the early 1990s. The one rolling off the production line in the year 2030 will use microprocessors made in the early 1990s. Why? Because you can update that microprocessor and it will correctly run the software, but the behavior of the system will change. I guarantee it. Okay? Because the software, in fact, doesn't specify the behavior. It's just incomplete. Okay? This, to me, is a profound embarrassment. Okay? I think that our engineering tools are just not up to the job. We do have beautiful ways of abstracting away the details of the hardware, right? You got a microprocessor. Well, we have an instruction set architecture, so you don't have to worry about which version of the microprocessor you're dealing with. You can put in a bytecode interpreter with a just-in-time compiler. That only has to worry about what the instruction set architecture is. The compiler that produces the bytecode only has to worry about the bytecode specification, et cetera, et cetera. We've got all these layers of abstraction. They're beautiful, right? And for the engineers at Boeing, every one of these layers of abstraction failed. Okay? The implementation, the design is actually the implementation. There is no design on paper. There's just a design in silicon and wires. It's a prototype and hack kind of style of design. And it's not because those guys are incompetent at Boeing. It's because we haven't given them the tools to do it right. Okay? So we could try raising the level of abstraction and introduce something higher than this, but that's going to be really problematic because the foundations are missing any control over timing. Okay? So give you a story. This is an old story. This is from 2001. Okay? And microprocessors that are used in these kinds of systems have gotten a lot more complex since 2001. But is a beautiful story because these guys did an analysis of a piece of safety critical control software for an aircraft that was less than 2 pages of code. Okay? Less than 2 pages of code. Running on a particular microprocessor. They had to construct a very detailed model of the CPU in order to be able to come up with a formulation of the worst case execution time problem for the chunks of code that we're executing.
So what's WCET?
Worst case execution time. Okay? The problem that they report in this paper turns into an integer linear program, a rather large one, okay? Rather difficult to solve, okay? Capturing the precise interactions with the cache, etc. Interestingly, they had to make a bunch of assumptions. One of the assumptions was that there was no I/O happening, okay? That's interesting. Why do you care about timing? Because you care about the interaction with the outside world. But you can only say something about timing if you're not interacting with the outside world. Okay? This is absurd. And this is the situation that people are in right now who are trying to design these systems. They have this fiction, worst case execution time. All the theory people who do, the prioritized scheduling always say, oh, assume you've got worst case execution time of this chunk of code, and then you can come up with scheduling policies. But of course, you don't have a worst case execution time. It's a fiction. Now, the fact is that the electronics on which we build computers is actually capable of delivering very precise and reliable timing. It's the software abstractions above it that discard that capability. Okay? So this takes me to the next notion, which is maybe we really need a temporal semantics in programs. Okay? So how would we accomplish that? I contend that actually the only rigorous way to accomplish that is to look through the whole abstraction stack and try to take this property that the electronics technology actually is capable of delivering reliable and precise timing and figure out how to expose that at the programming model level. Okay? So we started a project like this a few years ago that was focused on control over execution time. And the key idea of this project was that given that the hardware is capable, right, how can we get that capability exposed in the software? So we came up with a name for the project, which is PRET. Okay? It's a beautiful acronym because it means several different things, at least 5 different meanings. It's precision timed processors, or predictable and repeatable timing, or performance with repeatable timing. You can always get repeatable timing if you don't care about performance, right? You just way over engineer the system. That's, by the way, how it's done today. Okay? Enormous headrooms in the designs because there's no other way to do it today. The fourth meaning is, of course, the French word for ready, which has a timing notion, and the Dutch word for PRET means fun. It's a fun project. Okay, so there's significant challenges with this, and there are really computer architecture challenges, right? How do you design deep pipelines while maintaining control over timing? How do you get memory hierarchies without getting the uncontrollable variability that cache misses cause? How do you do I/O? The primary mechanism that uses I/O, the primary mechanism providing I/O is interrupts, and interrupts are enormously disruptive to timing and extremely difficult to control. Okay, so we have shown that these problems are all solvable. Okay. And again, it would take a whole talk to explain it. We've created 3 generations of PRET machines. The most recent one, in my view, kind of sews up the problem. And in fact, we declared this project finished in 2015, last year. And we've been trying to get people in industry to pick up on it to commercialize this. But this is a RISC-V-based open source implementation of a PRET machine. And the interesting thing about this implementation is that it demonstrably has no performance cost. Okay? In fact, it has slightly better performance than a comparable RISC-V processor under the assumption that you've got enough concurrency to be able to keep the pipeline busy the full time. Okay? Then you actually get a performance improvement. But again, it would take a whole different talk to talk about it. What I'd like to do is explain really what the benefits are. If you can get control over timing at the instruction set architecture level, you can improve the determinism of programs. This is important for cyber-physical interactions, but I also believe that it's important for concurrent software, okay? If you can get repeatable behavior out of concurrent software, that could be a very valuable property. And if you can control timing, you can get repeatable behavior out of concurrent software. You can achieve hard real-time with a lot less over-design. You don't need all that engineering headroom, which, by the way, can significantly reduce your energy cost because you don't have to clock your processor at 2.4 gigahertz. You just have to clock it fast enough to meet your real-time constraints, okay? And it can significantly reduce your costs. It offers the potential for certifiable safety. So, in particular, to address the aircraft problem, you could have software that will, at its I/O boundaries, behave exactly the same way when you update the microprocessor, okay? Because you can control the timing of those external interactions, and consequently, you could actually certify the software rather than certifying the whole hardware design down to the silicon and wires.
Go up the layers of abstraction. How does it change the programmer's experience in terms of writing programs?
Wonderful question. How do you expose control over timing at the programming level? And interestingly, there's a lot of people who have tried to do this in the past. None of them, by the way, by actually modifying the architecture to actually give you control over timing. But nevertheless, there's a rich, extensive graveyard of real-time languages that all have a real-time semantics that we can learn from, okay? But in my view, the missing ingredient here, and the reason that these things never succeeded, is they were not built on a solid foundation. You didn't actually have control over the timing. You just had the illusion of control over the timing, okay? So, portable software, I mentioned that, and actually you can get improved performance because you can eliminate pipeline bubbles. You can get less synchronization overhead, right? If you can control timing in two independent processes, then you can control when they interact without having to use semaphores, okay? So for certain kinds of applications, you can really dramatically improve the performance and eliminate all that synchronization overhead. So anyway, I believe there's a lot of benefits to this. From a research perspective, we have basically declared this project finished, and my strategy at this point is to try to get industry to pick it up. TI is very interested. National Instruments has picked it up in the form of soft cores. So we're optimistic that it'll get out there in the real world before too long. Okay, so I'd like to spend my last 15 minutes on what I think is actually the biggest of these, okay, which is how do you get temporal semantics in networks? And this one, you know, I talked about the CERN White Rabbit project where they synchronize clocks, okay. Synchronizing clocks is a good starting point, but it doesn't really give you timed semantics in networks. The question is going to have to be, you know, if you have these synchronized clocks, how are you going to use them in networks, okay? So let me talk a little bit about that. So here is a very nice example of a cyber-physical system that uses a technology that's similar to what CERN is using. So I want to emphasize that this isn't just, you know, CERN's effort isn't just an esoteric little side thing that's happening somewhere. This is a printing press made by Bosch Rexroth, and it's a machine about the size of this room. And it has a couple hundred microcontrollers in it that are all networked using Cat5 Ethernet for the networking and running TCP/IP. Okay, this Bosch Rexroth started making this printing press in 2008, and at that time nobody in industrial automation was using Ethernet and TCP/IP because they weren't designed for that. They're not. You don't have control over timing. You use CAN buses instead, or some network that's specifically designed for industrial automation. But these guys said, well, no, actually we can use Ethernet and TCP/IP. But the key thing that they did is they ran this same clock synchronization protocol that CERN was using, okay, which runs over TCP/IP. And they synchronize the clocks on all of these microprocessors, and then they orchestrate the use of the network so that they never get packet drops. Packet drops in modern Ethernet networks occur because buffers overflow in switches. And if you can orchestrate the use of the network, you can prevent buffer overflows. Moreover, you can, by orchestrating the use of the network, you can get deterministic latencies. So you can now actually have communication over these microprocessors where they're orchestrating their actions in the physical world over a network that is using basically internet technology. Now, this idea of making this use of the network deterministic is really the key thing that I'd like to focus on for my remaining 13 minutes, okay? Because it's a very controversial approach. You know, when I talk to people about using deterministic models for cyber-physical systems, it rubs them the wrong way, okay? But I'd like to convince you that it's actually the right thing to do. So my claim is that some of the most valuable models that we have are in fact deterministic models. Okay, so what is a deterministic model? Well, a deterministic model is one where if you're given an initial state and you're given the inputs, then the model defines exactly one behavior. This is a pretty vague definition because in order to nail this down, you have to define state, you have to define inputs, and you have to define outputs, okay? Or behavior, rather, okay? These things have to be defined, and if you define them formally, then you can determine whether a model is deterministic or not. If you don't define them formally, this definition is meaningless, all right? My claim is that deterministic models have proved extremely valuable in the past. In fact, I think they underlie the Industrial Revolution and the information technology revolution. So some examples, I already mentioned instruction set architectures. Instruction set architectures are a deterministic model of an underlying non-deterministic system. Why is the underlying system non-deterministic? Well, ultimately, it's electrons sloshing around in silicon and metal, right? That's what it is. And any particular realization of a microprocessor has really no assurance that it will correctly execute the software that it runs, right? You can get an alpha particle that'll flip a bit in the program counter and all hell breaks loose. The physical world is going to exhibit non-deterministic behavior, but the instruction set architecture defines a deterministic model that overlays that non-deterministic physical reality, and it's proved extremely useful. It gives a very solid target for a compiler designer, for example. All right, in cyber-physical systems, does it make sense to use deterministic models? So if you look at the Bosch Rexroth printing press, it's got some microprocessors communicating over a network fabric and interacting with a physical plant. By the way, the paper flies through this printing press at about 100 kilometers per hour. Okay? The ink is deposited at micron precision on that paper as it flies by. The paper roll that feeds the printing press is about 2 meters in diameter and weighs a couple of tons. And when the paper roll runs out, you don't want to shut down the printing press. The printing press ideally operates 24/7. It's just cranking out books constantly. Okay? So when the paper roll is getting small, a forklift comes in, loads a paper roll on a spare spindle, and then the computers spin up the new paper roll so that its speed matches the old paper roll. And then just before the old paper roll runs out, this device called a flying paster lays down double-sided tape, glues the new paper to the old, and it feeds it through and cuts the old, and then feeds it through without missing a beat. And all of this happens so that the seam occurs between pages of whatever's being printed, which was uploaded to a website as a PDF file. Okay? Very tight orchestration required to pull this off. And if something goes wrong, well, it can be disastrous, right? So you have to design these systems to anticipate all kinds of possible failures in the physical plant. Okay, so you've got these computational platforms, network fabric, physical plant. There's lots of sources of non-determinism in here. You could get packet losses. You know, Bosch Rexroth managed to get rid of them. Unknowable delays. Well, again, they were living in a walled garden, right? So their Ethernet wasn't connected to the internet. And so that made it a lot easier to do that. You have uncontrollable scheduling in the computational platform, unknowable execution times. Of course, whenever you interact with the physical world, you have imperfect actuation, you have parts failures, and you have physical noise. Lots of sources of non-determinism. So a lot of people come to me and say, well, all right, given all these sources of non-determinism, it doesn't make sense to even talk about deterministic models for these systems. You should instead assume non-determinism and design your system to be robust and tolerant of this non-determinism. I don't buy it. And the reason I don't buy it is because there's a distinction between models and reality. Okay? What is the role of models? Well, here's a model. This is Newton's second law, F equals ma, describing the dynamics of a physical object under forces. Okay? And this is a physical realization. So the model is constructed in a modeling framework, in this case, the calculus of Newton's laws. And the fidelity of the model is how well the model and its target match. Right? Okay. Engineers often confuse the model and the target. They think they're talking about the model, but they're actually talking about the target or vice versa. Okay? And there's a famous quote that you probably heard by Solomon Gulam from USC, who famously said, "You will never strike oil by drilling through the map," to emphasize that it really is important to keep the distinction between the model and the thing being modeled. I'd like to point out that this does not in any way diminish the value of a map. Okay? It's just that you have to know whether you're talking about the map or the desert. They're two different things. The map, of course, is always wrong. Its fidelity is never perfect. So another famous quote comes from Box and Draper, who have written a lot about the use of models in science and engineering. And they say essentially all models are wrong, but some are useful. Okay? You'll never get perfect fidelity. So if we're not after perfect fidelity, the question is, can we make deterministic models of these kinds of systems that are useful? Right? We're not trying to make models that are right. That's not possible. We're trying to make models that are useful. Okay? So we should draw on the best available models, right? Of course. We've got a whole tradition on the cyber side, a whole tradition on the physical side. Let's see if we can use the models that people have come up with there. Well, from this perspective, software is a model. And single-threaded imperative programs are, in fact, a deterministic model. Notice that in order to call them a deterministic model, I have to eliminate time, right? The time at which the input arrives is not relevant. The time at which the output arrives is not relevant, okay? And under those assumptions, within that modeling framework, single-threaded imperative programs are, in fact, a deterministic model, even though the underlying physical system really is never deterministic. I mean, there's always Murphy's law to contend with, right? Now, this particular deterministic model depends very heavily on the instruction set architecture model, which is also a deterministic model. And the ability that compiler designers have of constructing correct compilers depends on the determinism of both of these models. Okay? We really wouldn't have the compilers that we have today if these models were not deterministic. The instruction set architecture depends on another underlying deterministic model, which is synchronous digital logic design. This is a Intel Haswell quad-core chip with a GPU, so 5 cores on each die, 1.7 billion transistors here, okay? Worked on the first tape out. No errors, right? Relying very heavily on the determinism of this model and the ability to create silicon structures that are faithful to the model. Notice my weird turn of a phrase. I built a physical system that was faithful to the model, rather than building a model that was faithful to the physical system. That's what Intel does when they design a chip. They build a model, and then they build a physical system that is faithful to that model. Now, what about the physical side of cyber-physical systems? Well, we also have deterministic models. They're very powerful. They're very useful. Differential equations are used by mechanical engineers as the bread and butter of how to design the dynamics of a system. These are deterministic models. They are, like all other models, wrong. And the target is a non-deterministic system. The essential problem for cyber-physical systems is this one. You take the best deterministic models from the cyber side, and you put them together with the best deterministic models from the physical side, and the combination is non-deterministic, always. Because these models say nothing about timing. These models are all about timing. As soon as you put them together, you've got a non-deterministic model. So we don't have deterministic models for cyber-physical systems. Determinism? Really? Does it make sense to insist on deterministic models? So, in science, the value of a model lies in how well its behavior matches that of a physical system. Right? That's why we build models. But in engineering, the value of a physical system lies in how well its behavior matches that of the model. If I give you a piece of silicon that doesn't behave like that synchronous digital logic circuit, it's a piece of junk. Okay? These are complementary uses of models. Now, I contend that most scientists and most engineers use models both ways. An engineer will use models in the scientific sense, where you're trying to construct a model of the physical system and you need it to be faithful. And a scientist will use models in the engineering sense. They'll construct a model of something they want to build to control that Large Hadron Collider, and then they'll build it. Okay? So both styles of modeling are used in both science and engineering, but they are different uses of models. And it's important to understand which use of models you're using. How are you using your models? Okay? So here's a model of Newton's cradle. You can tell that it's a model because it's too perfect, and it's beautifully rendered in this nice graphics engine that does the shadowing, and it's overlaid on top of a copy of Newton's Principia Mathematica. It's a simulation model. And here's a real physical system that I bought on Amazon for $6, and it's a piece of junk. Okay? So to a scientist, if I write down Newton's laws of motion to describe this, the model would be flawed. It doesn't describe the behavior of that piece of junk that I bought. But to an engineer, the realization is flawed, and I should have been willing to spend more than $6 on Amazon to get something. And I confess, I'm an engineer. I'm more interested in the latter interpretation.
What's flawed about it?
What?
What's flawed about it?
About the model or the realization?
Missed something.
Didn't get going.
Oh, look at this.
It's kind of crappy looking.
It's just sloppy. I mean, it's the balls in the middle are supposed to stay still.
Oh,
Not really.
I see, okay.
Yeah, it's supposed to work like this.
It's horrible.
But it's hypnotizing, it's nice.
Well, yeah, okay. I guess it depends on what your goals are, whether it's actually achieving them. Okay, so for cyber-physical systems, I think we need to change the question. This is, of course, a time-honored tradition in academia. If you don't like the answers you're getting, change the question. So my claim is that the question is not whether deterministic models can describe the behavior of cyber-physical systems with high fidelity. Okay, I think if we ask that question, the answer today is no. Deterministic models cannot describe the behavior of these systems with high fidelity, and hence we're stuck with Boeing's approach of stockpiling the microprocessors for 50 years. Okay? But if we change the question to this one, whether we can build cyber-physical systems whose behavior matches that of a deterministic model with high probability, I firmly believe that the answer to this question is yes. Okay? And I also claim that, well, what about resilience and adaptability? Deterministic models don't eliminate the need for robust, fault-tolerant designs. Every system is going to be subject to Murphy's law. In fact, I would claim that deterministic models enable such designs because they make it clear what it means to have a fault, right? If you have a deterministic model, you have a clear definition of what a correct behavior is. You now know what an incorrect behavior is. It's the complement of the correct behavior. If you can detect that, you can adapt to it and react to it. Okay? If you don't have a deterministic model, what do you mean by a fault at that point? That's a problem. Now, I'm pretty much out of time, so I can't really tell you an existence proof, which is another project that ended last year that we called Ptides, that showed, in fact, that you could design cyber-physical systems that start as a deterministic model for which we do have a faithful realization that is cost-effective. Okay? The key idea is that it uses time-stamped events on streams, and that the timestamps acquire a global meaning through synchronized clocks. Okay? So specifically, if we can assume a bound on the clock synchronization error, 80 picoseconds for CERN, 1 microsecond for us mere mortals, okay? We can assume a bound on network latency. Then we can ensure that events are always processed in timestamp order. So we get deterministic streams. If in addition, we can assume bounds on execution time, for example, using PRET machines, then we can also ensure that events are delivered to actuators on time, and consequently we can get deterministic interactions with the physical world. Now these are three strong assumptions, right? What if the assumptions aren't satisfied? So here's non-synchronized clocks right here on the Clark Kerr campus, okay? Again, we need to understand the distinction between the model and the thing being modeled, and the fact is that anyone who designs these cyber-physical systems is already making these assumptions. It's just they're not making them explicitly, okay? They need the same assumptions. We're trying to make those assumptions explicit, okay? And this also clarifies what a fault is. Okay, so from my perspective, these are 6 possible interpretations of what real-time is. 2 are very uninteresting. 1 is unachievable with today's technology. That leaves 3, all of which I believe are really quite interesting and require a lot more work, of course. So my claim is that the foundations for real-time computing are really weak today, like this piece of crap engineering. And we have existence proofs that a sound notion of real-time computation is actually possible and practical. Thanks.
$6 on Amazon.
Yes.
Well, this is a very disturbing talk because it shakes the foundations of many of the algorithmic models that we work on. Certainly the streaming level that you talked about is very relevant to what this whole meeting and program are about. But I wonder whether you really need timestamps. You have all of these logical models which involve partial order on operations or assertions about how certain things will never happen, but without the need to have a clock exactly. And I'm wondering...
Yeah. I think for many applications you don't need timestamps, and so I believe there's a large class of systems where you can just live in the world of streaming data without associating time to them. But that does not include cyber-physical systems, which is a very large class of systems. And the reason it doesn't include them is that cyber-physical systems fundamentally have an interaction, and usually it's a closed-loop interaction. And you're interested in the closed-loop dynamics of the system, not just the open-loop dynamics. So it's the CERN talk yesterday was all about collecting data. There was no closed loop. There was no effect on the physical world, okay? If you're just collecting data, then yeah, you probably don't need, well, you might want timestamps just to know when things happened. So you might still want timestamps, but they're not an essential part of the semantics anymore.
So actually my question was very similar, and you sort of answered part of it, but still I understand that you need time for the physical world, and internally maybe you just need the order that matters. But is there some sort of abstraction where, you know, because the time from the outside world is not going to be necessarily completely precise. Timestamp is going to have some.
Absolutely. Yeah, but of course all models are wrong. So
yeah.
any model of time you construct is going to have, you know, some mismatch with the physical world. But you raise a very good point, which is that when you're within the world of computation, most of the timing actually doesn't matter. In fact, the only place that timing matters in computation is when you're interacting with the physical world. This observation, by the way, is completely missing in almost all of the papers that you read in the classic real-time computing world. You know, they talk about scheduling tasks, and they talk about the timing of these tasks, even when the tasks have no interaction with the physical world. Well, who cares what the timing is? You really only care at the boundaries between the physical world and the computation. And so Ptides, the model in Ptides does that, okay? In fact, the only place that timing comes in, the connection between timing at the physical world is that if you have a sensor wrapped by software, you timestamp its data using your local clock, okay? The clocks are synchronized, but not perfectly. So you have to have a bound on the clock synchronization error to understand how the overall semantics works, okay? Similarly, at actuators, we deliver timestamped events. And those timestamps are interpreted as a command to the actuator to perform an action at a physical time corresponding to the timestamp according to the local clock. Everything in between is now an untimed computation. The timestamps are still there, they're carried through, and they're part of the semantics of the execution, okay? But when the execution gets done is irrelevant, at least modulo delivering the events here to here on time. Yes?
So you mentioned at some point that we might soon have networks with near perfect clock synchronization.
Yes.
What do you expect to be the practical implications of that, or some of them?
Well, among other things, you can orchestrate the use of networking. So think of the way, for example, that we use Wi-Fi today, right? It's a wild west. You turn on your radio and you start transmitting and you collide with everybody and you back off and you try again, right? Think about it if you play tennis, right? Suppose that we allocated tennis courts that way, right? You would need a lot more tennis courts in order for anyone to really be able to play tennis without waiting around for enormous amounts of time, right? So you have to over-engineer systems, and you lose capacity due to this lack of orchestration. But if you have synchronized clocks, you can orchestrate uses of shared resources. So you could design distributed software in a very different way if you could rely on your clock being synchronized with all of the other pieces of software that you're interacting with over the network. So Google did this. Google
systems to become synchronous, fully synchronous?
No, they're not fully synchronous. That's a mistake. So Google actually reinvented this same technique, Ptides, and published it in 2012, describing a system that they call Spanner. Okay, and Spanner is a distributed database system. It's meant for databases with replicated data that are in different data centers. So imagine that you've got a data center in Seattle and a data center in Dallas, and both of them are getting queries. So for example, a query comes into Dallas asking whether an airline seat is available, and a query comes into Seattle trying to reserve the same airline seat. Okay? What should the database do? Both Seattle and Dallas have copies of the current state. Okay? So in Spanner, what they do is they synchronize the clocks in Seattle and Dallas using the same technology that CERN used, okay? IEEE 1588 Precision Time Protocol, and they timestamp the queries. And now they define the semantics of the database to be dependent on the numerical order of these two timestamps. If the timestamp in Dallas is lower than the timestamp in Seattle, then Dallas should respond that the seat is free. Okay? Otherwise, it should respond that the seat is occupied. Now, the question is, how should Dallas respond? Well, with this technique, all that Dallas has to do is it timestamps the query, and then it watches its local clock. And when its local clock hits a threshold, it responds that the seat is free. Okay? It doesn't have to communicate with Seattle to issue that response. So it's a beautiful technique that it does orchestration over networks without communication. So if you have synchronized clocks, you can coordinate without communicating, which is a very powerful thing. Yeah.
That's in a completely different direction. Given the complexity of the input space and the behaviors possible inside a physical system, is it possible to even imagine a succinct model description of what you want to achieve and then start to build the model, process the model?
I believe it is. In fact, these Ptides models are built as discrete event simulations, and they build on the very long tradition of simulation. Okay, people have used discrete event simulation back since the 1970s to describe the behaviors of complicated systems. You build the model as if it were a simulation. You can run a simulation, okay, but we treat it not as just a simulation, but as source code. So we then compile that model into something that's executable on a platform, and we guarantee under the assumptions, the three assumptions, synchronized clocks with bounded error, bounded latency, and bounded execution time, under those three assumptions, the compiled code will behave exactly like the simulation.
Let's take remaining questions. Let's take remaining questions offline and take the speakers.
Thank you.